Maskata, can you we are recording. So today after the class, we are going to have a bonus that you are here. We are going to demonstrate something nice or something beautiful that I hope you will like it. Okay, so from last time we talked about the magnetic monopole. We talked about the magnetization vector and also how the magnetization vector can be used to determine the current density or the induced current densities. And okay, so let's continue. Okay. So let's not forget, we are dealing with the current densities. I don't show so much part. Acabo de ser abdul de pernas se estudaram o efeito screening. So we are over with electrostatics. We are doing magnetostatics, and from here we are using a law which relates the 4 pi dl prime over r. So from the current density, we are finding the A. From then here we are finding the B, and B is going to look something like this, divided by 4 pi 1 over r squared dl prime cross product with AR, and what AR is let's say if this is the infinitesimally small current element, which we denote this one as dl prime, the AR, it would be the direction from the current density toward, so this is going to be some angle alpha, so this is going to be AR, this direction. At the same time, we can have another infinitesimally small current element dl prime, and again, here this is alpha 1, this is going to be alpha 2, this is going to be the unit vector along the AR. So more or less, this is the representation of these equations. And from these, so this is all we can say for the moment. Pretty soon, we are going to discuss the Maxwell's equations, where the electric field can be created, so electric field can be different from 0 in case delta B over delta T is different from 0. Now, whenever this new electric field steps into our equations, we are going to do another overview of how all of these quantities are related with respect to each other. Now, whenever we are at this topic, we said from the very first week of the class that one of the most essential elements when we are doing these topics is the dimension analysis. So we always try to check the units step by step, what they are, how they change, etc. And the second part is that after the dimension analysis, we want also to, to analyze carefully the direction of these vectors. So for a moment, I just want you to provide some partial insight into the possible geometries that we may be faced with. Okay, let's assume for a moment. So far we have thought about how to find the fields that are associated with currents that can be pointing in this way, which this means that the current is equal to I0 times AZ. Okay, we use this symmetry. The current is going along the Z direction. In the coordinates that we are dealing with, if it is cylindrical coordinate system, if this is cylindrical, we are talking about coordinates R, phi, and Z. This means that we have unit vectors along the AR, unit vectors along the A phi, and unit vectors along the AZ. That's good. Now here, what is the direction of the current? I. How would we denote it here? What is the direction of the current I? Which one?
From the bottom to top.
That's correct, but
AR.
which one of these unit vectors would you select?
AZ.
Now, AZ is this one. This is pointing along the Z direction.
A5.
A5, that's correct. So I is equal to A0, A5. That is true. Okay, that's good. Then, so these are completely two different configurations. And then let's have a look here. The A, it looks like it is going to be the same direction with the current I. And one thing that might remind you of this relationship is the following. AX, this component AX, is going to be equal to mu 0 IX, okay, divided by 4 pi dl over R. AY, it's also equal to mu 0 current along the y-axis divided by 4 pi integral of dl prime over R. So why do we write this down? We write this down because we can say that the magnetic vector potential, it is going to be equal to A times AZ. Immediately, we can also say this A is going to be equal to some magnitude, because every vector quantity, it has a magnitude, it has also the direction, and the direction here is going to be A5. Okay, that's good. So far, so good. Which means that if we are at some point P here, so this is the current, where is the magnetic field vector potential? A. This is A, okay? We found it, it should have the same direction. Yeah, in the other case, if the current it has this direction, if you want to find at some point P, what is the magnetic field? So A, it will have, it is going to have something like this. So this will be the direction of the A, okay? It will be circumferential, I'm going to call it like this, but the A phi, it tells everything. Now, at the same time, we can also try to distinguish what is the direction of the B as a function of the direction of the current. Now, at this stage, we might say that the direction of B it is going to be perpendicular to the current I, but probably this might be a little difficult to figure out, but what can make this easier is that the B, it is the curl of A. This is always true, okay? So I think we remember this one, right? We used to say that if we have a scalar potential V, from this we can get the electric field, which is equal to minus the gradient of V. If we have some magnetic vector A, the B, it will be equal to the curl of A. So both are fields. This is intensity, this is flux. They should not be confused. But both of them are space derivatives of two different potentials. This is a gradient, in fact, this is the curve. Good. Now let's remind you about something essential. If we have two vectors A and B, what can you say about the vector C, which is equal to A cross B? What can you say to this? We might say that C is going to be perpendicular to A and perpendicular to B, right? C is perpendicular to A and C is perpendicular to B. We expect this. And how do we do the cross product between A and B? We can say that this is equal to, here I, JK, this is AX, AY, AZ, BX, BY, BZ, and each respective component along the three coordinate systems, this would be equal to I times, you know, like the determinant of this little thing, which is AY BZ minus AZ BY, and so on. So this is how we do this, right? And then we have the other component, which is equal to minus J, and this is AX BZ, AX BZ minus AZ BX, AZ BX. Good. we have also the third component. We are good at finding the cross product between two vectors. At the same time, when we do this type of curl of the vector A, what are we expecting? We have here AR, A phi, and AZ. Now, that was Cartesian coordinate system. This is cylindrical. What should we include here? This is d over dr, the derivative with respect to r, d over d phi, d over dz, and here we have ax, auy, sorry, no, we should write here ar, a phi, and az. That's good. Now, we know I, we found A. We know I, we found A. Now we need to find B. B, it is going to be, since B is equal to the curl of A, that means that B, it will be perpendicular to A. How is this possible? Let's write this one AZ. This is possible saying that B, it is going to be equal to BR times AR plus B phi times A phi. Okay? So if you have three orthogonal different directions, R phi Z, represented by unit vectors AR phi Z, if A is this, B, which is going to be perpendicular to A, will have components along these two units, right? Along these two directions. So this is something which, before thinking that this is pretty complex, we should have enough intuition to pick up the direction of these vectors right away. Okay? And then similarly, here we might say that for now we go to the other configuration, the B, it should be equal to what? Now A, it is A phi. So A, it's here now. So if A is here, that means that the B, it will have projection along these two units. So B will be equal to BR times AR plus BZ times AZ. So that's where we're going to find the B. Now, so far we are good. This is something which, even if you come to an oral exam, this is something which you should never forget, because you are going to need this piece of information when you deal with antennas. Students of antennas that are taking this course, they always, most of the time, it happens that they forget about this fundamental discussion that we are having right now, because when they do the antennas, they often have an antenna right here, and they have to figure out what is the direction of the electric field and magnetic field at a very far distance. But if you remember just this one, so you just need to know the current, you find these. And now another important element, which we're going to see pretty soon, is that we're going to observe that the electric fields, they can be proportional to the curl of B. Okay? So in that case, we have not done this one yet, but I promise. Have we seen this relationship? I will. Actually, we have not seen this so clearly, but we've seen this. We've seen that E dot dl, this was equal to minus the rate of change of the magnetic flux as a function of time. I believe we have seen this, okay? Or maybe we'll solve a couple of examples regarding this. Now, whenever the electric field is represented like this, we can say that the electric field in this case is going to be perpendicular to B. If it's going to be perpendicular to B, this electric field, it will look pretty much like AZ, and here the electric field here it will look A times A phi. Now these were some short overview of possible configurations of currents from where we have to determine the A and the B using these equations. Now, last time we talked about the magnetization, and let's jump into this aspect right away. So the curl of B, it will always be equal to the free current density plus some induced current density, which is because of the magnetization over the volume. So this whole thing can be written J plus the curl of M. In this case, what we can do is that we can take this curl to the other side, and we're going to have 1 over mu 0. So 1 over mu 0, you can bring this B divided by mu 0 minus the curl of M. This is equal to the free current density. The good thing is that this operator is a linear operator. Okay? The derivative is linear, which means that, what does linear mean? Linear means a function h or k, a plus b, this is equal to this linear operator k applied on a plus linear operator k applied on b. So this is what these linear functions mean. So we can not substitute we subtract the magnetization vector from the b divided by mu 0, and this whole new term, we can write this one as the h, which is the magnetic field intensity. And at this stage, we just do the curl of h. This is equal to j. Now, if we have the curl of h equal to j, we can immediately report or expect that the direction of j to be perpendicular to h, okay, or the other way around. So they are perpendicular with respect to each other. And we also, whenever we see such a relation, we do remember the Stokes Theorem and what was the other one? The divergence theorem. The Stokes Theorem, it reported that the curl, the integral over a surface of some curve, it's equal to the integral over a line. So here we can write the curl of h integrating over meter squared. It's going to be equal to the JDL, okay? Or at the same time, this can also be written as the curl of h dot dl. But these two are equal. Then at this point, so if this is j, we can also write the j here, and then we can ask the question: what is the unit of j? This is measured in ampere. So let's write this one amp per meter squared. This is a surface, because we know that Stokes theorem, it is some curl of some vector a times meter squared, and this is a, same vector, times meter, right? So this is two-dimensional integral, it drops down to one-dimensional integral, or line integral. So if this is a per meter squared times meter squared, we cancel out the dimensional analysis. It tells us that the current I, it is equal to the integral, sorry, here we have this is a mistake. Let's try to pick up the mistakes we have on the board. So first of all, this is the current, this current is equal to, sorry, this is true. And based on this, we can write this, and at the same time, we can also, so far we are good, which actually this, based on the unit, this is the current, and this is going to be equal h dot dl. So okay, so this is a unit law, and a similar law to this one, we have seen it before, which was the following. We used to have the PDL was equal to what? So we have this relation, but now we have this new expression, and the B, it is a magnetic field flux, and the H is a magnetic field intensity. Now, since we are talking now about the intensities and the fluxes, if you remember, we used to have a similar discussion when we were dealing with the electrostatics, where we had these kind of relationships, that the displacement vector, it was expressed as a product between the permittivity of the medium times the electric field. A similar expression we are going also to observe in the case of the magnetic field flux. So this is a flux, and this is equal to mu times h. Okay, so this will be the case, and at this stage we can. So this is. So we can put here a mu zero. If we are in vacuum, this is true. But if we are in some other material, we can, in general, we can express the magnetic field. It's equal to the, let's write it like this, mu zero times mu r times h. At the same time, we used to have epsilon zero, epsilon r times E. This is permittivity of the vacuum, and this is the relative permittivity of a new material. Why would one need to have such relationships? This would be needed. For example, if you want to have a capacitor and we want to store a lot of energy to this capacitor, what we can do is that we can fill the region between the two capacitor plates by new material, because the risk in those, it is that we can have a huge electrical discharge through one plate to the other, the same way that you see the thunder, because you have an electrical discharge from one cloud to the other. And in order to decrease the probability, what we can do, we can fill this up with disa materiale që nuk është përcjellës. Për shembull, për të mundsuar që kapacitorat të operojnë në ngarkesë më të mëdha, çfarë bëjmë? Marrim dy pllaka paralele, mes fusim copa letrat. Pa letrat e relative permittivity këtë elementin, këtu e ka më të madh se njësh. Ose fusim gomë. Shpesh kapacitoret vendosin është një material ceramik si puna e pjakës. You fill it like this. If you go to the lab, you find the capacitors. There is some ceramics around it, which enables for two plates for them to be charged without them being discharged from one positive charge plate to the other. Okay. Now, a question that you might always expect from me is this: what is the unit of this? Çfarë njësie ka kjo permittiviteti relativ? Exact, është kish numër. Sepse ke numër, sepse ti ke gjithmonë që njësia kësaj ka njësi çka ka. Kjo është shumë vërtet do t'jap dëm. Kjo është numër, nuk ka shans tani të jetë të ngrej diçka katror. Pra, nëse kjo është numër, po kjo çfarë njësi ka kjo? Atë numër është vërtet. Pra dhe kjo është numër, por pra kemi këtë relacion, në përgjithësi mund të themi që kjo B-ja është e barabartë me permeability të ambientit, që shumëzon intensitetin e fushës magnetike. Pra nëse kemi po e quajmë kështu, DE BH, këto të dyja janë flukse, kjo është intensitet, kjo varet nga ngarkesa, kjo varet nga rrymët. Pra mund të shikojmë të pikturën e përgjithshme në këtë formë dhe shpesh atë që mundohemi ne të shprehim në këtë tonë është që gjithmonë fluksi në shkallën e hierarchisë, it is more fundamental than intensity. Why do we care about this one? Because if we have a difficult problem, we always think that working with quantities which are constant across different regimes are better to work with. Që do të thotë, nëse kalojmë nga ambienti 1 në ambientin 2 në ambientin 3, janë disa masi që janë konstante gjithandej. Edhe ne aty duhet kapim, ne kemi qenë shumë të kapim të konstante, pasi ta zgjidhim problemin bazuar në atë. Ashtu siç na pëlqen të dikur të mbahemi për energjisë që është konstante në shumë ambiente të ndryshme. Përdorim konservimin e energjisë edhe gjejmë gjithë ekuacionet e televizies. Përdorim konservimin e impulsit, gjejmë se çfarë do të ndodhë. Në këtë rast, fluksi nga që është një masi pak më stabil, ne na pëlqen shumë fluksi për e krahasuar me intensitetin. Një arsye tjetër për këtë është që fluksi Edhe nëse kujtojmë për kufizimin e fluksit, atëherë i heqim gjithë dyshimet. Fluksi përkufizohet si numri I vijave të fushës. Do të thotë që këtu kam një ngarkesë, edhe këtu dalin 3 vija fushë, për shkak se është ngarkesë e vogël. Po të ketë shoqë këtu të baga parë një ngarkesë që është 2 fishë, sa ajo ka 6 vija fushë. Të vjetë e fushë që është shpërndan deri në infinit, këto njësojnë çdo vit. Po do të shërmosh 3-3-3. Kjo është një masi që mund ta interpretojmë që një konstante, por intensiteti nuk e ka të shprehur. Ecim atëherë. Tani në lidhje me vlerat që merr kjo myrëja ose kjo the value of the relative permeability, this determines whether material, so let's write it like this. So mu R can make can distinguish between a material which is diamagnetic. So mu R, let's write it like this, slightly smaller than 1. We can have mu R, which is slightly larger than 1, and here mu R, it's huge. Okay, so we can have these 3 cases. The first material, it is diamagnetic. The second one is paramagnetic. Here, paramagnetic, and this is ferromagnetic. Ferromagnetic, which means it has to do with ferro. This means that these are materials which can be magnetized, and they are constructs or units which are very helpful in coils or in solenoids. Që kemi bobina për mësuar transferimin e fluksit magnetik nga një pjesë në pjesë tjetër, ne përdorim përcjellëse. Hekuri është një përcjellës shumë I mirë që përdoret për këto konstrukte, dhe bobina tradicionalisht ne kemi në njërin krah kemi një rrymë I, në krahun tjetër kemi një rrymë I2, tu kemi një numër bobinash në mish, tu kemi një numër rotullamesh for the number of coils is equal to N2, and often we want to transfer the magnetic flux from one side to another. So from here, this is some magnetic flux which is created. We call this V1. Here we have another magnetic flux. And now a good question for you, and I expect the students that are sitting on their backs at home to answer this. Pyetja për gjithë është kjo: a vjen dot një elektron nga fierza deri te shtëpia juaj? Çfarë mendoni, ha? Se ha? Se?
Larg shumë.
Është larg shumë. Po të presim.
Presim 2 milionë.
Jo, sa shpejtësia e elektronëve në tela? Është 1 mm për orë, nuk është shumë, pak. Pra elektroni nuk është e vjen, po presim për një kohë të gjatë. Edhe dikush që është në shtëpi, a vjen elektroni nga fierza deri te shtëpia? Po te koka erdhi. Për shembull, po ta marrim një elektron, po ta ngjyrosim me ngjyrë të kuqe, a do e shohim kur do vijë shtëpia jonë? Çfarë mendoni? Jo, pse?
Është I vogël shumë.
But the small particles, they move faster than the heavier particles. So if there is something to come here, the lighter ones will come first. Keni edhe përgjigje nga shtëpia ju?
Pra, ideja me transformator me bobinën, ajo rryma nuk do jetë e njëjta rrymë e parë, do jetë si rrymë I nduar, përcjelluar nga fusha magnetike. Dhe sepse do jetë elektroni pa. Nuk do të ikë.
Kjo është vërtet një elektron e fierza, ne nuk do vjen dot kurrë, sepse gjatë gjithë rrugës ne kemi ka shumë transformator. Voltazhi vjen 220 volt, nga 20 volt do shpërndajnë stacione që ulën deri në disa mijë volt, deri 220 volt. Për shkak të këtyre bobinave, ky elektroni që është këtu ky shkon kthehet bashkë në fierza, edhe vjen po këtu, por nuk kalon dot tek shumë saktë. Pa një elektron që vjen nga stacioni ku prodhohet energjia, nuk vjen dot deri te shtëpia jonë, për shkak se kemi të transformator, të cilët funksionojnë me materiale ferromagnetik, sepse dëshirojmë që fluksi të transportohet sa më mirë në mënyrë sa më efektive. Nuk na pëlqejnë shumë këto, pavarësisht se kanë këto vetitë e tyre. Që çuni I thotë të ballet e aluminit nuk është magnetik, do habita ka shpejtë thotë pota, po nuk është rrofsh. Pra, disa materiale që përdorin kuzhinë, disa janë magnetik, disa nuk janë, që do të thotë prandaj tenxherët nuk I bëjmë për hekurit, sepse për shkak të nxehtësisë do na gjeroni shumë elemente të padëshirueshëm, etj. Dhe the chain with immateriality being between a diamagnetic and paramagnetic is essentially the difference is that we can have the electrons. One of them it relates to the spin or the rotation of the electrons around the nucleus, and the other one it has to do with the rotation of the electrons around themselves. So here we have the spin, which is the number S. Here there is the orbital number L, which rotates around the whole nucleus. Now, this topic we can switch. For example, we have diamagnetic materials, which are copper, silver, gold. Paramagnetic is aluminium, titanium, tungsten. And let me see for a moment. We have copper, silver, gold. Okay. Now, it is always good. So I looked at the Mendeleev table, and it looks like these elements, they are all below each other. So in the transition metals, if you watch the Mendeleev table, this is where these three are located. So it looks like the effect to choose between a metal, whether it is diamagnetic or paramagnetic, it has to do a lot with the outer number of electrons in the outer shell. Asta electronul care trebuie să ia așa e aticton de valența electronului. So you can read in a book that there are these, but you have to go back to the table, look at them, and they belong to the same group. Okay, that's good. So these are all diamagnetic, so they belong to this family. Now, all of these, the properties of a specific material, they greatly depend on these, also for reasons which has to do with the existence of magnetic monopoles at the micro scale. In the macro scale, you can assume that metals often they create these little loops, and these little loops, effectively, they're going to create this little M, okay? And when a lot of these loops are aligned with respect to each other, so they are all aligned, we get a magnetic material, okay? So if we have, in micro scale, they are always there. In macro scale, if they all add up to the same direction, we get a magnetic material. Okay, so then we can get magnetism. So for metal, you can put it into a magnetic field, and you can kind of align all of the magnetic dipole, and iron can become a very good magnet, okay, even though it's not initially. But what can happen is, if you heat up the iron, what will happen here, this will be disordered. You're going to increase the entropy in the system. Okay? Entropy is a term which is measured to quantify chaos or to quantify disorder. So if you have some disorder in the system, you're going to increase the entropy. If you have disorder in the system, that means that you're going to have some dipoles this way, some dipoles this way, and some dipoles in this way. So overall, we are going to lose the magnetization. And the disorder, it's a factor which increases with increasing the temperature. So for many materials, if we heat them up, they are not magnets anymore, which means that if you pick up a magnet which is sticking to your refrigerator, you just heat it up a little bit, and then it will not be a magnet anymore. So this is because all of the materials, they have a temperature which is called the Curie temperature, temperatura Curie's. And above this temperature, if this is higher than Curie temperature, then magnetization vector, it converges to zero. Okay. So we should stay away from very high temperatures, and that's why in transformers, where we want a very effective transfer of the magnetic flux, we need to cool this down a lot, because once they get hot, things don't perform at the expected behavior that we'd like them to behave. Okay, so these were some elements regarding the behavior of the magnetic materials in sexual. Okay. The next topic we have to talk about is the boundary conditions. Boundary conditions, we've seen this quite a few times. The first time we talked about the boundary conditions, it was when we had the electric field and the electric displacement vector, and we had to figure out how they change from one side of material 1 when we step into the material 2. This was the first time we saw boundary conditions. The second time we saw them all together, it was when we solved the Laplace equation and the Poisson equation that looks something like this. And this was, again, boundary condition. We were saying that one wall, we can give it a potential V1, at another wall, we can give it a potential V2. Find what is V as a function of X. Find this. This was the second time. Now we are seeing again the boundary condition, and at this time we are going to have a similar discussion like in here. We're going to have medium 1 and medium 2, and we will see how the fields in magnetostatics are related from one side of the material to the other. So we'll see how this one and this one, or which component of B and H are conserved on the two sides of the system. Now, regarding these, all we need to do is that we need to implement two postulates, right? So, what do the postulates report most of the time? They report, so please don't forget these. The postulates, we always report what is the divergence and what is the curve. Okay? So this is what we always use. Okay? That's we report the divergence, and the divergence of the magnetic field. This was equal to 0. This was equal to J or mu J. And now the first one, which reports the wait a second. So actually, this one, you can also write this one as the, we can write here the H, and this can be written equal to J. So we can take out the permeability, and we can write down the intensity and not the flux. And now, I want to ask you, do you remember when we did the boundary conditions for the electrostatics? Which component, which perpendicular component was conserved from medium 1 to medium 2? Do you remember?
The sides one.
Which one?
The sides from
For the E, the tangent.
The tangential one, but for which quantity?
For the E.
For E. That's good. Okay, so that's right. So before we used to see that E1 was equal to E tangent 2, and the D normal one was equal to D normal 2. Actually, if we had some current density at the surface, this was not conserved. Okay, but the thing is that let's assume that at the boundary we had no extra charges. Now, intensity flux, a similar boundary condition we're going to see also here for the magnetostatics. But regarding these, let's do this after we give a short break. Okay.